conformations of acyclic alkanes. So we know already that this bond right here between the two carbons in ethane, that's CH3CH3, is a sigma bond. So this is a sigma bond. And it's made up of an sp3 overlap. And it's basically this line connecting both nuclei, this carbon, first carbon on this case on the left, to the carbon on the right. The one thing we need to remember is that this bond right here rotates. So you see this arrow right here. This indicates that this bond rotates, and it's rotating at room temperature all the time. Well, it's not without consequences. What's going to happen is it's going to have implications on the stability of this whole compound that this bond is spinning. So in this case, as we said, the two methyl groups, like this is the first methyl group, this is the second one, are not fixed in a single position, but are free to rotate about the sigma bond connecting the two carbons. Well, this is what we call conformations, is when this bond is rotating between the two carbons, the arrangement, the spatial arrangements of the atoms are going to change, and that's what we call conformations. So notice how, for now, this H is up on this side, it's down. If you rotate, once you rotate, they might be both up now on each side. So again, you see here a different spatial arrangement happening as you rotate the bond. You will see this with more pictures. So here it is. Imagine this is what we had here. If you can superimpose the H's, you will see that these small spheres right here, those are the hydrogens, and of course the big ones are the carbons. And here's the rotation that is occurring. So again, you have rotation at this bond right there. If we were to say, okay, what happened as we rotate this? Let's actually have a point of reference. So if we rotate, you leave this untouched and you rotate and this one moves. Let's say this is right here, our blue sphere. Notice where it's going to be now at. It's going to be down there. So kind of make that rotation in your mind. Again, this class requires lots of visualization. So there you go. So now the location, this is the new location. After rotation. So again, this is a conformation. And this is another one, a different conformation. So we can say this conformation 1 and this is conformation 2. So the names are given for two different conformations. We can't call them the same. So as you notice here, we say conformation 1 and 2. Well, we have a name for them. We have what we call staggered, a conformation. The CH bonds on one carbon bisect the HCH bond angle on the adjacent carbon. Okay, so there's a lot of words here, but we're going to see that down here because it doesn't apply as well on these two, I would say, representations. So this representation, especially from this angle, is better. So and then they have another one, you have what we call an eclipsed conformation. And this eclipsed conformation, you have the CH bond on one are directly aligned. That's the whole point of eclipsed, are aligned with the CH on adjacent carbon. So what does that all mean? Of course, we couldn't do this without some representations. So one way of doing it is you're viewing this from the left. Okay, so the view is from the left. And if we just do something very, very simple, if we kind of tilt this up, move this up, and if you can imagine it in your mind, you will see that you actually have this carbon right there is the front one. And the back carbon right there, that back carbon is actually no longer seen. It's kind of hidden. So let's actually write this down. We're going to say that this back carbon, it's actually right there in the back, but it's hidden. So what's hidden is that, again, this back carbon. So there's an easier way of drawing this rather than just simply working on it with the CH and the skeletal structure. We have a new representation that we call the Newman projection. Now, let me just tell you again, as I've been saying all along, is that in this class, in order for you to be very successful, you have to be able to use these different representations and translate between them. So it makes sure that you understand, you get a more holistic understanding of the concept. So here we have the ball and stick. Now let's actually use we don't have the ball and stick all the time, so we have to use the Newman projection. It's actually very, very easy. What you do is you draw a circle. And what you want to do is you put a dot in the front. And in this case, look how I'm going to superimpose it. If you didn't pay attention to what happened here, you would think that this carbon has 6 hydrogens attached to it, but that's not true. What happened is, again, this carbon with this 3 hydrogens are actually, they're all hidden in the back. So what you do is, right here, if we trace it, this carbon right here has this H, that H, and this H. We extend them right there. Okay, so it may not be the best way to draw it because it is not like pen and paper, but I will try one more time because, again, it's a very critical. It's good that I'm practicing too. But again, here we go. It's not working this time. So here we go. As you can see. And now the carbons in the back, I'm going to use red here for the hydrogens. Notice how this is up. right here. Now, this is called a Newman projection. It's an easier way of drawing it. There are a few things you need to remember about the Newman projection. Number one is that the front, as we said, the front carbon is a dot. So front C is a dot. Sometimes actually the dot is not shown. It's just implied that it's there. Back carbon is that circle. That's why we draw that circle. Otherwise, if we just put two dots, one would be on top of the other one. So the back carbon is your circle right there. And then the most important thing is this angle that is between these, as we said here, HCH bonds. So again, HC, all right, H bonds. So this case, this is what we call a dihedral angle. And we use theta for this, and it's a 60-degree angle. And that's 60 degrees. And there's a name for this. This is what we call a staggered conformation. Right here. So the angle again is a 60-degree angle. And that's again in a staggered conformation. Now let's go to the other one. The other one is where you have the eclipse. So once again, if we do a bit of tilting here, we need to tilt this up as we did with the previous one. So let's go back to the blue here. Tilt up. Once again, you see how now the hydrogens are aligning on each carbon. And now again, if you did not know there was a carbon in the back, because now it is tilted up, you would not know that there are 6 hydrogens, right? You would think there are 3, and maybe some kind of a mistake here, but that's not true. So to do this, what you have to do is, again, draw a circle as we did right here. Now, to draw this, once again, the front carbon right here, this front carbon, is a dot. And it looks like a Mercedes sign, if you remember the Mercedes symbol. Again, here are the H's. Again, I like to be a little bit more of a perfectionist here, but it's not as easy to draw it using this tablet than in class. But we'll do our best. It's not as easy. Let me move this up a little bit. Okay, so there's your H. Now, you'll see it on the next page. They look much better than my drawings. Now, to do the ones in the back that are not shown, what you do is you kind of want to give it an angle, although there is no angle, but we do that for the sake of showing that this is an eclipsed. So what we do here is we kind of move the H in the back that's not shown, like let's say this one right there. Move it a little bit behind like this. Like to put the H down there So in the back, you don't see it. Right there. And of course, this H that's not shown in the back, a little bit up. This has an angle. So you might look at the angle and you say, okay, well, what is the angle between these bonds? And the angle is actually, so the angle is 0. There's an angle of 0. And this is an eclipsed conformation. And it is the highest in energy, and we will explain why. So this is where we're at now.